All right, welcome back to our Chapter 8 physics video. And we left off talking about torque. And the important thing to remember about torque is the line of action of the force vector that causes the torque has to be perpendicular to the line from the point of rotation to the point of application. So in this example here, FA is perpendicular to that line. Let's just say, call it the door. So FA is perpendicular to the door. Its full force multiplied by the length of the door will give us the torque. FC is diagonal. It has both vertical and horizontal components. Its vertical component multiplied by the length of the door will cause torque. And FD, because FD is 100% horizontal, and that line of action is passing right through the hinge, that's not going to open up the door at all. That we need some component of the force to be perpendicular to the door in order to open it, and FD just doesn't have that. Now, an alternate way of looking at that is that if we look at the diagonal force FC, maybe we could extend that imaginary line of action to some point here in space where we can measure a distance from the hinge to that line of action such that it makes a perpendicular right angle, and then we can multiply the full force by whatever this radius is. So that is also a way to find the torque caused by FC. I, however, prefer finding the y or vertical component of FC here and then multiplying it by this radius or r, the length of the door. I think that's easier to do. So here we go. T, or tau, I should say, tau. So this is a good example of how I'm always encouraging students to think in terms of the Greek letter. And don't call this T. Don't think of it as a T. Think of it as tau. Tau is torque, and that's equal to the radius r, and it has this perpendicular subscript indicating that the distance from the point of rotation and the force being applied, that those two lines, the line of action of the force and this imaginary line here, they need to be perpendicular to each other. So it's the perpendicular distance times F, whatever this force is. Okay? So let's look at an example problem where we have a skeleton with a bicep muscle attached to it, and the muscle is capable of exerting a force up of 700 newtons. And here's the actual hinge, the actual point of rotation, and it is 5 centimeters away from where that force is being applied. So if we simplify this diagram, it's basically like this. We have a 700 Newton force that is making a right angle, and it has a radius of 5.0 centimeters. Now, centimeters is not the standard unit we like to use, so we should convert that. 5 centimeters. For every 100 centimeters, there is 1 meter, so we're going to divide this by 100, which means we're going to move that decimal place 2 places to get 0.05 meters. So we've got 0.05 meters. Let me get rid of that line. Okay, there we go. 0.05 meter is the distance, or the radius. The force is 700 newtons. And so torque is equal to this radius times force. And so that's going to be 0.05 times 700 which equals 35 Newton meters. So the units of torque are unit of force and distance. The textbook calls them meter newtons, but that just sounds weird to me. I've always used Newton meters. But either way, it's like potato, potato. The order doesn't really matter so long as you have a unit of force multiplied by a unit of length. All right, let's do a little substitution game here where we start off with Newton's second law of motion. Force equals mass times acceleration. Okay, but if we relate our acceleration, linear tangential acceleration, to rotational acceleration, that relationship is A equals R times alpha. So we could take this R times alpha and substitute that in place of A. So that means that Newton's second law now becomes F equals mR alpha. And if torque is equal to Fr, then we can say that torque equals mR alpha R, because what we're doing is we're taking this mR alpha, which is related to force, equal to force, substituting it in here for this force, and so now this becomes mR alpha R. And then if we just combine the two R terms, R times R is R squared, so we end up with torque equals mR squared times alpha. So this is just a different way of writing Newton's second law for rotational motion. So whereas before we had F equals ma, now we have the sum of torque equals the sum of mR squared times alpha. So this is something we can use in the future to solve some problems. And we're going to move on now to an idea or a concept called moment of inertia, the rotational moment of inertia. So if I were to come up with an analogy between this and something, a concept for linear motion, it's somewhat similar to mass. Like if there was a big rock or let's just say a box on the ground, and I told you to go over there and pick up that box. If it had a very large mass, it would be difficult to pick it up. If it had a small mass, it would be pretty easy to pick it up. So with objects that we want to spin in a rotational fashion, it is the same thing is true. If it's more massive, if it has a greater mass, it's going to be harder to spin it than it would be if it has a small mass. But it's not just the mass that makes a difference, but also how that mass is distributed. So if, for instance here, let's assume that these two cylinders have the same mass, but one is a long, skinny cylinder, and the other one is a short, flat cylinder. Well, this one is going to be harder to spin because more of its mass is located farther away from the center of rotation. It's flattened out more, has a bigger radius. If the radius is bigger, then the moment of inertia gets bigger. And so the moment of inertia is essentially describing how hard it is to spin that object. So if we have a higher moment of inertia, it's going to be harder to spin that object. And we have a table, this comes right out of the textbook, of how we can calculate the moment of inertia for various shapes. So we have it for a thin hoop. That's going to be mR squared. And that's if we're spinning it about the axis that goes through the hoop. If we're going to spin it through an axis that goes through its diameter, then that's a different moment of inertia. The distribution of the mass with relationship to the axis is different. So then that becomes 1/2 mr squared plus 1/2 mw squared, where w is the width here. Haha, so there is a w. So we don't want to confuse this with omega. This is w, not omega. And then we have a solid cylinder with a radius. It's at 1/2 mr squared, or a hollow cylinder, and so on. I won't read the whole table to you, but this is an important reference for doing homework problems, especially involving rotational motion. Depending on the shape of the object, you'll need to refer back to this table in order to know how to calculate the rotational moment of inertia for that particular object. All right, let's do some more of this little substitution game here. So we had said in a previous video, or a previous slide in this presentation, that the sum of torque is equal to the sum of mr squared times alpha. And generically speaking, the moment of inertia is equal to the sum of mr squared. So if this is like if we broke the shape down into a bunch of little tiny pieces, and we took the mass of each of those teeny tiny little pieces and their distance from the center, and we did mr squared, and then we added it up for all those tiny little pieces, that would give us the moment of inertia. And so we can substitute this in. The sum of mr squared is equal to I. So we could just say all this is I. So basically what we're saying then is that Newton's second law of motion for rotational motion is that the sum of torque is equal to I alpha, moment of inertia times angular acceleration. All right, let's see if I may not get all the way through this example problem in the time I have remaining, but I'm going to go ahead and start it. So what we have here are two situations where we have a pair of masses, a 5 kilogram mass and a 7 kilogram mass. And they are located 4 meters apart. If we wanted to spin these about an axis that is right in the center of them, so in other words, we've got a 2 meter distance here and a 2 meter distance here, what would be the moment of inertia for this system? Versus over here, we're going to spin the same two masses, 5 kilogram and 7 kilogram, and they're still 4 meters apart. But instead of rotating them about an axis in between them, we're going to rotate them about an axis off to the side here. So this one's going to have to rotate like this, and this one's going to have to go all the way over and around and back. So as you can imagine, this second part B is going to be more difficult because this 7 kilogram mass has to travel a much longer path. But we're going to prove mathematically that that is the case, that this is easier to rotate than this, even though the masses are the same. The way they are distributed with relationship to the axis is very different. So we want to calculate the moment of inertia for each of these two systems. So for this system, the generic formula for moment of inertia is that I is equal to the sum of mr squared. So we're going to treat these two masses as just simple points. They're not spheres or cubes, they're just points in space. And so I is equal to 5 kilograms times 2 meters plus 7 kilograms times 2 meters. And it looks like I am just about out of time, so I will have to resume in the next video.